Hi everyone, today I'm going to talk about recent work on combining cluster number counts and two-point correlation functions. I'm Chun-Hao from Stanford. The content of this talk is based on our recent papers, and it's going to be unlocked very soon. So if you are interested in the content of this talk, please do check our paper. Okay, before I go into the details, let me give some motivations why we even want to combine the galaxy cluster number counts. In this plot, I'm showing you the number of galaxy clusters as a function of their mass. Three different colored curve corresponds three different universes that have three different sigma at, which is the cosmological parameter that describes the amount of structure in the universe. From this plot, you can see that the number of galaxy clusters are very sensitive to sigma A, and it turns out it's also very sensitive to omega m, which is the amount of matter in the universe. However, also from this figure, you can see that if you have a small amount of error in the mass of the galaxy clusters, then you will have a huge error in their abundance, and therefore you will also have a very huge error in your cosmological parameters. So the accurate mass calibrations is very essential for the cluster cosmology. In this project, we use the bias of the galaxy clusters as a tracer of the galaxy cluster mass. And how we measure that? Here is an image from the dark energy survey. First, you can see there's a galaxy cluster here. You can cross-correlate the position of the galaxy clusters and the shape of the background galaxy. This is called the cluster lensing. The idea is that the shape of the background galaxies will be distorted by the gravitational potential of the galaxy clusters. So by measuring the amount of distortion, you can use that to measure the mass of the galaxy clusters. On large scale, this two-point correlation functions is proportional to the bias of the galaxy clusters. Also from this figure, you can see there are many other things. For example, you have the galaxies that's at the same redshift of the galaxy cluster. So you can cross-correlate the position of the galaxy cluster and the galaxy. This cross-correlation is called the cluster-galaxy cross-correlations, and it's proportional to 1 power of cluster bias times the galaxy bias. You can combine this with the galaxy clustering, which is the autocorrelation of the galaxy itself. These two, you can basically calibrate out the bias of the galaxy, and you will get the bias of the clusters. Further, you can also calculate the autocorrelation of the cluster clustering. So basically, this is the autocorrelation of the galaxy cluster. The signal is proportional to the bias of the galaxy cluster square. So all these four two-point correlation functions will give you will be some tracer of the bias of the cluster, and it therefore can be used to calibrate the mass of the cluster. Okay, now I'm going to present the data vector in this project. So in this project, we consider the cluster abundance and combine that with 4 two-point correlation functions. So first, we have the galaxy clustering, and you have 3 cluster-related cluster two-point correlation functions, mainly the cluster-galaxy cross-correlation functions, the cluster lensing, and the cluster clustering. The samples we consider here for the cluster sample is the optically selected galaxy clusters, the red mapped clusters, and the galaxy sample we considered is the red magic galaxies. On the figure here, I'm showing you the covariance matrix of this project. So this is to demonstrate the size of the work. The area covered by the red square is the 3x2 point covariance matrix, and all the other elements are developed in this project. In this talk, I'll focus on the terms that's in this blue box. I want to highlight a couple of differences between this analysis and the DSY1 cluster cosmology analysis, or the traditional cluster cosmology analysis. Okay, so in a traditional cluster cosmology analysis, people usually do a two-step analysis, meaning that they measure the cluster lensing. They model the cluster lensing signal to get the mass of the galaxy clusters. They then joint model the mass and the number counts of the clusters to get a cosmology. In our analysis, we adopt a one-step approach, which we simultaneously model the abundance of the galaxy clusters and the two-point correlation functions to get the cosmology. The reason we do this is because then our result is easier to be combined with other cosmological probes, like the 3x2 point analysis. Further, the traditional cluster cosmology use a lot of small-scale informations. The traditional analysis go basically model the weak density signal down to 0.2 H-inverse megaparsec, while in our analysis, we focus entirely on large scale, meaning the 2-Hale term. The reason is that our analysis will be saved from many small-scale systematics, like baryonic effect or miscentering. However, since we only use large-scale information, this degrades some of our cosmological constraints, but this amount of information loss is saved by including multiple two-point correlation functions, like the cluster-galaxy cross-correlation functions and cluster clustering. And I'll show you later that our cosmological constraints is competitive compared to the traditional cluster analysis. A large part of this project is we validate the analysis pipelines on the simulations. So the philosophy we take is we simulate a galaxy catalogs, and then we treat the marked galaxy catalog as a plausible universe, and we then run through our measurements or the analysis pipeline on that to get a cosmology and check whether we can recover the input cosmology. All right, so first I'll talk about some simulation setup. We know one of the most important systematics for the cluster cosmology is, especially for the optical cluster cosmology, is the projection effect. We therefore create spatial versions of the buzzer simulations so that the range of projection effect in the simulations will span the data. This can be shown in this plot. So in this plot, the y-axis I'm plotting here is a proxy for the projection effect as a function of the redshift. The reason we choose this proxy as z is because we can directly measure it on the data. This is shown as the black line. So the black line with the arrow bar is the measurement on the DSY1 data. And the three different color curve correspond to three different simulations. The buzzer A, the orange line, is the one that have this amount of projection. And the buzzer B, which is the blue line, that have the largest amount of projection. And in both of these two simulations, we have 10 DSY1 realizations. The green line corresponds to buzzer C, which we have one DSY3 realization. All right, so this is sort of a first chart of our analysis. In this paper, we performed the first end-to-end validations of the cluster abundance analysis on the catalog level simulations. So what we do is we first have an input cosmology. We run gadget to get the dark matter simulations. We then run AGLs to get the galaxy catalog. We treat this galaxy catalog as a plausible universe. We then run through our cluster finder, red mapper finder, the galaxy finder, the red magic galaxy algorithm, the photo Z code, the BPZ, and the shape measurements, the Mach meta-calibration. From this algorithm, we get 3 catalog. We have the source galaxy catalog, including the velocity, and we have the RedMapper cluster catalog. We have the RedMagic galaxy catalog. We then run our measurement pipeline to get the data vectors. From theory, we can also get the covariance matrix. And with the data vector covariance matrix, we can infer the cosmological parameters. Then we can compare that with the input cosmology to see whether we can recover it. All right, let me now show some results. Before I show the cosmology result, I'll show some our investigation on the systematics. In the simulations, we find there are actually some systematics, and this is usually called the large-scale selection effect. The reason is that there is some correlations between the richness of the galaxy clusters and large-scale correlation functions at a fixed cluster mass. And this correlation leads to an additional bias we call the selection effect bias. This selection effect bias can be actually understood as some kind of, so the concept is very similar to the assembly bias of secondary Hale bias, which is a manifestation of the correlation of some local Hale properties with the large-scale correlation functions at a fixed Hale mass. And here, the local Hale property we have is the richness. The reason why we call this the selection effect bias, not the assembly bias, is because this bias is much larger than the theoretical predicted assembly bias. And we believe that this selection bias is because the RedMapper algorithm, but not something physical. We can measure the selection effect bias on the simulations. What we did is you can measure the cluster galaxy cross correlations. Basically, you run through your RedMapper finder on the simulations. You can calculate the RedMapper galaxy cross correlations. Because it's in the simulations, you also know the mass and redshift distribution of those RedMapper clusters. So you can randomly select the Hales that have the same mass and redshift distributions. Then you compare the cluster galaxy cross correlation of the RedMapper clusters and the random Hales. The extra clustering of the RedMapper clusters is basically called the selection bias. The bottom 3 plot, I'm showing you our measurement on the simulations. So the y-axis is the selection effect bias, and the x-axis is the scale. So from these 3 plots correspond to 3 different simulations. You can see that in these 3 different simulations that have different amount of projection effect, on large scale, the selection effect bias is scale independent. Therefore, we can model it by a relatively simple model. Our model have only 2 parameters that describe the normalization. So basically the absolute value of this selection effect bias and the mass dependence. So we marginalize it over these 2 parameters while we constrain the cosmology. So in all the result I show later, we basically marginalizing over these 2 parameters. Right now, here is our main result. What I'm showing you here is the 68% and 95% contour on sigma A and omega m. The dashed line here is the true cosmology that we use to generate the simulations. The blue contour is the expected DSY1 uncertainty. The orange contour is the combination of 10 DSY1 realization. So effectively correspond to a survey that's 10 times larger than the DSY1 survey. Okay, so 3 different panels correspond to 3 different buzzers. The first one is the one that have this amount of projection. The second one is that have the largest amount of projection. And the third one is the DSY3. We have only 1 realization. From this figure, we find there's a 2 sigma level systematic. Basically, the systematic is not statistically significant. But we can actually also test whether this 2 sigma level systematic is due to flaws in our causal analysis. To check that, we perform the 2x2 point analysis, meaning you simultaneously model the Gaussian clustering and the Gaussian lensing. And then we can compare the recovered cosmology with to the one that's recovered from the causal analysis. From the figure here is the result. So the orange and the blue line is the same as the previous sites. On top of that, we add a green line, which coming from the 2x2 point analysis. So from this figure, you can see that 2x2 point analysis and the causal cosmology analysis have basically consistent cosmological constraints. So let's basically demonstrate that the deviation doesn't come from the flows in the causal analysis, and it could come from the just the zero fluctuation or some problem in the simulations. To distinguish between these two possibilities, we leave this to future work. Okay, so other than the end-to-end simulation analysis, we actually also stress test our model by using the simulated likelihood analysis. So in the simulated likelihood analysis, we analyze the systematic contaminated theory data vectors. We consider 3 systematics. So the first one is indicated by the DS collaboration, so the DSY1 cosmology analysis, that the mass of the Gaussian clusters from the causal lensing is low. So we therefore make the one Hale turn causal lensing 50% lower than the expected value to see whether we can still recover the true cosmology given this systematics. Then we consider a nonlinear bias. We also consider the specific functional form of the richness mass relation. We show that basically showing in this plot that none of the systematic can bias our cosmological constraints by more than 0.5 sigma. So we therefore have confidence that our analysis is robust to these 3 systematic. Okay, I promise you I'll show some comparison of our constraining power with the traditional causal analysis. So here it is. We run our analysis on the DSY1 data. The result is shown here. Is still blinded, and we plan to unblind this very soon. So stay tuned. But in this figure, you can see that it's a sigma I omega m contour. The blue contour is our result, and the orange contour is the traditional causal analysis. So you can see the constraining power is comparable, and I want to note that the area and redshift range of our analysis is slightly smaller than the DSY1 causal analysis. This is because we want to have a joint footprint between our analysis and 3x2 point analysis, so we can combine these 2 analyses. So the slightly larger contour is because this difference in the area. Okay, so here's my conclusions. In these papers, we build a method of combining cluster abundance and 2-point correlation functions. We then validate our analysis on 3 different versions of buzzer simulations, and in all of that, in all the simulations, there is no significant systematics. We further stress test our model by various systematics to show the robustness. And some of the highlight of this work is that our work is set from small scale systematics, and it have competitive cosmological constraints, and it's relatively easy to be combined with other cosmological probes. Thank you.